Hello everyone, today I'm excited to introduce our ICCV 2025 paper, LatentReframe, Enabling Camera Control for Video Diffusion Models Without Training. This work is done by Zheng Hongzhou, Jian, and Jebolo from University of Rochester. Video diffusion models have recently shown amazing power. They can generate realistic, high-quality videos purely from text prompt. However, one big limitation remains: we can't easily control the camera. So what is camera control video generation? Given a target camera pose trajectory, we want the generated video to move exactly along the trajectory. For example, to pan, to orbit, or zoom according to the predefined path. And this shows more results about the camera control video generation. If we want to do camera control, most existing methods require heavy fine-tuning on a large paired dataset of videos and camera poses. This process is slow, computationally expensive, and often breaks the prediction model's learning distribution. So our question is simple: can we achieve precise camera control in video diffusion models but without any extra training? Nowadays, 3D reconstruction models are very powerful. They can recover 3D or even 4D information from 2D videos, and such 3D or 4D information can also be rendered back into 2D videos. So later ideas arise: can we use a reconstruction model to guide the video diffusion model, letting the diffusion model generate the content, while the reconstruction model provides geometry control? That's how we arrive at LatentReframe. Let's see how it works. First, consider a normal video diffusion model. Given initial noise, it gradually denoises to produce the clean video. During this process, we can obtain an estimated video x0 and any intermediate time step t. However, this denoising process itself has no explicit camera pose control. Suppose we already have a desired camera pose. For example, we want the camera to rotate slightly to the left. How can we change the video's viewpoint accordingly? To solve this, we propose latent reframing. When we get the partially denoised video x0 at time step t, we feed it into a point cloud estimation model to reconstruct a time-aware point cloud, that is, one static point cloud per frame or line over time. Then we render this time-aware point cloud from the target camera pose to generate a reframed video that follows the desired camera trajectory. However, this rendering introduces many blank or black regions caused by occlusion and incomplete geometry. So how can we fill these missing parts and obtain a complete videos? For this, we propose our second key method, latent rehabilitation. We use the video diffusion model itself as an independent model. We reintroduce noise into the reframed videos, but with different noise levels. We add more noise to the unknown regions and add less noise to the low regions. Then we continue the denoising process. This lets the low regions guide the unknown regions, producing a complete and high-quality result. We use Monster to extract the time-aware point cloud. It produces globally aligned point maps and per-frame camera pose. We then compute the target pose from realistic 10,000, normalize them, and rendering using Python 3D. As you can see from this figure, we add stronger noise to the unknown regions and weaker noise to the low ones. This allows the low content to guide the missing part during denoising, so the models can naturally fill in these blank areas and generate smooth, complete videos. In our implementation, we apply latent reframe in the inference stage. For example, with 25 denoising steps in total, we perform reframing around step 8. At that point, we estimate the time of our point cloud, rendering the reframed video, and add noise differently for low and unlow areas, and continue denoising. By step 11, both regions reach similar noise levels, and then the remaining denoising is applied uniformly. Finally, we obtain the complete video aligned with the target camera pose. Next, let's look at our experiment. Our method achieves comparable or even better performance than training-based method in both video quality and camera control accuracy. In terms of FID and translation errors metrics, our method performed the best. We also conduct several ablation studies, like time-aware and static point cloud. Time-aware point cloud successfully capture motion, such as head movement or ocean waves, while static one fails. As for the reframing step, performing reframing at 0 step with no noise causes artifacts. and performing it at 16 steps with higher noise will reduce the point estimation accuracy and leads to unstable result. Step 8 can achieve the trade-off. We'll also compare noise reduction strength. If the difference between low and high regions is just step, artifacts appear. If it's too large, like 5 steps, the result becomes blurry. A 3-step difference gives the clearest and most stable result. As for the point cloud extraction model, monster produce more accurate time-aware point cloud and poses than the master and master, which often show artifacts or pose errors. Then we will show more results. This slide shows basic translation trajectory, basic rotation trajectory, different video styles. We also apply our method on DIT and ULAB-based video diffusion models. We'll also extend our method from text to video to image to video, and also higher resolution and longer video generation. To summarize, we propose LatentReframe, a training-free method that enables camera control for video diffusion models. It consists of 2 key components, latent reframing and latent rehabilitation. Our approach achieves results comparable to or even better than the training-based method. Of course, there are still limitations. Large camera motions may fail due to the missing regions, and the result depends on the accuracy of point cloud estimation and the basic video diffusion models. That's all. Thank you for listening.